Heavy Charge Center in Diamond. So as you can see, we have our dopant, we have our 300 coordinated nitrogen vapors.
Right. That's oxygen.
This is oxygen. Well, all of our dopants were chalcogens, right?
Right.
And Dr. Stolbov, he actually he had a really smart idea that because the triplet is like 2 empirical electrons, one in the ground state, one in the electron state.
Right.
That's an even number, right? So we're not considering the semicore S electrons. We're considering only the p valence electrons in regards to the formation of this defect. We have some that are hybridized that are bonded. Then around the dangling bond, we have your spin links, localized electrons, right? So you remove a boron from the system, you remove 1p electron, right? And then nitrogen has 3p electrons. You replace it with a chalcogen like oxygen, sulfur, selenium has 4p electrons. There's a net loss of 0p electrons through the formation of the defect. So that's an even number, right? Like a triplet, which make the number of electrons in a triplet, which make it favorable for triple formation. That's actually what we found. There are kind of contingencies like this. Selenium is kind of a hypothesis. It's a larger atom, so pushes the bond lengths around here pushes the atoms closer together in the system. The wave functions overlap, kills the magnetism, and it's a singlet. So that's the theory behind why that happened. But this is our most promising defect out of this, because we're trying to find spin qubits. We found excitations in our work up to 3 electron volts. So you want the band gap to be wide enough to accommodate that excitation. We also want to be isolated states so we can have coherent spin projections, reading and stuff. But the whole point of our work is not dealing with the reading out, the writing out, error correction, operations. It's more dealing with the reinitialization. So the reason we're finding these triplets is because we want to find a corresponding singlet for our favorite spin polarizations. So basically, you have your spin projections because it's spin equals 1, plus minus 1, which are degenerate, and then ms equals 0. You incite that. This is proof of a triplet ground state, which is the global minimum of the spin polarizations. Excite that to a triplet excited state, and then because you're going from spin 1 to spin equals 0, it's how can we reset these plus and minus 1 spin projections to 0, right? You have to make it a singlet. But we need a conservation of angular momentum to spin over coupling, J equals L plus S, right? So the spin goes down to 0, L has to go up, and that's going to be facilitated by phonons. So our phonon, all these are dynamically stable, but they'll have these max frequencies, roughly around 150 electron volts. So basically, there has to be this non-radiated transition facilitated by phonons from the triplet excited state to the singlet excited state. That'll be a higher energy than the singlet. And then there'll be an optimal transition down to the single ground state. And now everything's back to ms equals 0. And you go to the triple ground state. And that happens over and over and over again because of the non-zero probability that those plus and minus ones will be to the single state. And then ms equals 0. So this goes back. And then we reset it. So we have a promising spin polarization cycle for this. This is not so much. If you look at the GW density states, you can see something that's a little bit you don't want that. And that's right here. We have something over the Fermi level, a peak over the Fermi level, a little bit metallic. What we want is more like this. This is close to the valence band, but it's kind of isolated. Then we have isolated occupied state. We have these isolated unoccupied states. We can have a healthy excitation. Here, not so much. So this is actually a hint that we needed to do exaction, meaning what does this look like if we scale the supercell? Maybe this will move. I see. Maybe if we actually did see that it moved, changing these x and y coordinates, this actually did move.
How big is the unit?
4 by 4 by 3. But we did exaction with 5 by 5 by 2, 5 by 5 by 3. We went up to 6 by 6 by 2. And what we found is that this actually has a lower energy singlet. So the material is a singlet. But this is actually really promising. These are flip This is actually very exciting because we have these strong excitations, these ranges. I'd say the limit probably for a spin qubit is 0.2 electron for that spin polarization.
So what you're saying is do you be able to calculate whether it's going to be a spin active kind of state? So both of this or just this one, the spin active?
Yeah.
What was the question?
I was so do you know if the defect could be a spin active state?
Well, this one it is.
This one is, I was wondering whether those
This
two,
one,
those are
it
not.
depends on the concentration. If we large concentration, it looks like it is. And we don't know if this is can be checked experimentally, but it would be nice to see if it depends on the concentration, because once you reduce the concentration, basically you separate more your defects,
Yeah.
then it becomes a singlet. That's it. So, but we don't trash it because it at least for high concentration, we know it's a triplet, and it's a good triplet, by the way. And it can work as a swing qubit.
I see. Yeah. So normally, so I'm just speaking from my experimentalist kind of point of view. So,
Okay.
Because if we want like single photon meter, we were looking at single defect. So basically, of course, if you can do like a 10 by 10 unit cell would be the best, because that would be like the most like possible one. But it doesn't make sense, right? Because it takes a lot of energy and time, right? So, but like that's what we're looking at. Like if we could have like like this triplet in like only one defect, then of course that means that it's good. Then maybe it's something that we can do.
But
Yeah.
we have scaled this up to 5 by 5, and the physics doesn't change.
Yeah. So that's good.
Yeah, this is like this is good. But here, with that exaction, we found like Dr. Cardozo said that as it becomes less dense, it loses its triple state.
Yeah.
So it's not really that.
But that's
it's
we can still
it's-
check. We can still
Yeah, it's dynamically stable, and all these are thermodynamically favorable too. By the way, like
You mean like Wurtzheim BN?
yeah. I mean like all these defects. Like,
Oh,
they're
okay.
thermodynamically like this was like binding energy for this was like -10. This is -5, -3, and then these had increasingly like more positive formation energies in nitrogen-rich environment. They were positive, but they were like lower than 5, which is favorable for our purposes.
Yeah.
Pretty
because
much what
it's
would you get
controllable
for
to make.
the NV center in diamond formation
Yeah.
energies. So
That's
it's
good,
very
yeah.
feasible.
Yeah, like also like the one that you guys are choosing, oxygen, sulfur, selenium. Those are the one that we could basically be able to introduce in there. Like if anything, because we have like chemical, like say H2S, H2SE. Those are like active gas that we could use. It's like experimentally available. But the only thing I was worrying about just like how do we even get to Wurtzheim or nitride at first place? I just have no knowledge of it. Like, is it some material that people actively
Yes.
working with?
Yeah,
Yeah,
Wurtzheim
there's,
with
there's, a lot,
yes.
there's a lot of work.
Yeah.
Yes.
So maybe we can work on it. Like, is it? How do people grow it? Grow it like a